In previous videos, we saw how quantum mechanical models of the atom were developed to explain the observations in spectral lines. Niels Bohr quantized the energy levels of the hydrogen atom to explain the existence of and relation between spectral lines. Arnold Sommerfeld formulated a more detailed quantization rule to explain why spectral lines split in the presence of electric and magnetic fields. All these quantization rules and selection rules were put in a coherent theoretical framework by Werner Heisenberg with his matrix mechanics. Shortly after, Erwin Schrödinger developed wave mechanics. This theory is equivalent to matrix mechanics, but it uses familiar wave theory, rather than unfamiliar and abstract matrix calculations. However, there were also some observations that these models did not explain. For example, it was not explained why some spectral lines turned out to be 2 or 3 closely spaced lines when you look more closely. The anomalous Zeeman effect was also not explained. In the normal Zeeman effect, for which Hendrik Lorentz had given a satisfactory theoretical explanation, a spectral line would split in 3 when a magnetic field is applied. In the anomalous Zeeman effect, the spectral line would not split in 3, but in perhaps 4 or even more spectral lines, according to a pattern that was not yet explained by theory. Furthermore, the atomic models explained that an atom has certain energy levels that an electron can occupy, but they didn't explain why each level can be occupied only by a certain number of electrons. Why don't all electrons just occupy the lowest energy state? All of these questions will be addressed by the theory of electron spin. In the following, we will see how this theory was developed. First, empirical formulas were constructed to describe the fine structure and the anomalous Zeeman splitting patterns that were observed. Then, Wolfgang Pauli used these results to formulate a simple rule that explains why a certain energy level can be occupied by only a certain number of electrons. George Uhlenbeck and Samuel Goudsmit gave a physical interpretation of the empirical formulas. They concluded that the electron is spinning. Pauli then formulated the mathematical rules to calculate with spin, and incorporated spin in Schrödinger's wave equation. Before we look in more detail at how the theory of spin was developed, let's first go through some preliminary theory so that we can then better understand the discussion that will follow after. First, let's briefly recap the explanation that Lorentz gave for the normal Zeeman effect, which we discussed in more detail in a previous video. The experimental observations were the following. If we collect the light from a flame of a certain chemical element with a diffraction grating, then we can separate the wavelengths of the light. Each wavelength, which has a certain angular frequency omega0, will give a spectral line. When we put the flame in a magnetic field, the spectral line splits in 3. If we observe the spectral lines from a direction that is perpendicular to the direction of the magnetic field, we see that the central spectral line has a polarization that is parallel to the magnetic field, while the outer 2 lines have polarizations that are perpendicular to the magnetic field. If we view the light from a direction that is parallel to the magnetic field, we don't see the central spectral line anymore, and the outer 2 lines are circularly polarized. Lorentz explained these observations as follows. With Newton's second law, he calculated how the electron moves when it is acted upon by the Lorentz force due to the magnetic field. He decomposed the electron's motion in 3 components: a linear motion that is parallel to the magnetic field, and 2 circular motions, clockwise and counterclockwise, in the plane perpendicular to the magnetic field. These 3 oscillations were found to have different angular frequencies. The shift in these frequencies is directly proportional to the strength of the magnetic field and the ratio between the electron's charge and the electron's mass. These calculations were performed at a time when people were still not fully certain about the existence of electrons as particles. But if they were assumed to exist, J.J. Thomson could already calculate the charge-to-mass ratio from his cathode ray experiments. The fact that the charge-to-mass ratio found from the cathode ray experiments matches the one found from the Zeeman effect was convincing evidence for the existence of electrons and that they are part of atoms. So to conclude, Lorentz found a satisfactory explanation for the splitting and polarization of spectral lines by using the classical theory of electrodynamics. However, it was found sometime later that the electrons in an atom don't behave according to the laws of classical electrodynamics. According to the Bohr-Sommerfeld model of the atom, the orbits of the electron are quantized in the following way. Niels Bohr found that the electron can only occupy states of certain energies, and that radiation is emitted when electrons transition between these states. With this, he explained the spectral lines of the hydrogen atom. Arnold Sommerfeld then found that the shapes and spatial orientations of the orbits are also quantized. For a certain energy level, there are different shapes and orientations the orbit can have. The fact that different orbits can have the same energy is called degeneracy. This was used to explain why spectral lines can split when an electric or magnetic field is applied. Different orbits with the same energy will respond differently to an external field. So applying an external field will lift the degeneracy, which results in the splitting of the spectral lines. The quantization condition can be formulated mathematically by integrating the electron's momentum over its orbit. Because we can perform this integral over 3 dimensions, x, y, z, we can obtain 3 quantum numbers corresponding to the energy, angular momentum, and spatial orientation of the orbit. Degeneracy means that for each energy quantum number, there are multiple quantum numbers for angular momentum and spatial orientation. Now the question is, if these electrons don't follow the classical laws of electrodynamics, how can we explain with quantum theory the Zeeman effect that Lorentz had previously explained with classical theory? In the quantum theory, the emission of radiation occurs when an electron transitions between 2 energy levels. If no magnetic field is present, the 2 energy levels will have a certain energy difference, and the energy difference is directly proportional to the frequency of the emitted light. When a magnetic field is applied, the orbits with different orientations with respect to the magnetic field will undergo different energy shifts. The differences between the new energy levels are directly proportional to the frequency shift that Lorentz calculated for the normal Zeeman effect. To correctly predict the experimentally observed spectral lines, the following selection rules have to be introduced. First, the quantum number for the angular momentum has to differ by 1 between the 2 states. The quantum number for the spatial orientation can only differ by 1 or 0. If it differs by 1, the light has a polarization that is perpendicular to the magnetic field. If it differs by 0, the polarization is parallel to the magnetic field. These selection rules could later be derived from more fundamental principles in Heisenberg's matrix mechanics. We derived that in the normal Zeeman effect, the shift in angular frequency is proportional to the magnetic field strength and to the electron charge divided by twice the mass. This ratio occurs very often, and it is called the gyromagnetic ratio. As we will see in the following, this quantity describes the ratio between the angular momentum and the magnetic moment of an orbiting electron. Let's first explain what a magnetic moment is. Suppose we have a loop of conducting wire with a certain height and width. Through the wire runs an electric current. We will now see what happens to the wire loop when we apply a magnetic field in the plane of the loop. Due to the Lorentz force acting on the current, the 2 sides of the loop experience forces in opposite directions. The magnitude of the force is equal to the magnetic field strength times the current times the height of the loop. These forces cause the loop to rotate, and this source of rotation can be expressed as a torque, which is given by the force times distance to the axis of rotation. We can substitute the expression for the Lorentz force. We can express the torque in terms of the area of the wire loop. We can define the magnetic dipole moment vector as the current times the area vector. The area vector points in the direction that is perpendicular to the surface whose area it describes. The torque is then given by the cross product of the magnetic dipole moment and the magnetic field. By comparison to the standard expression of the torque, it is as if the magnetic field is a force that acts on an arm, which is the magnetic dipole moment. Now we consider the magnetic dipole moment of an orbiting electron. If the electron has a certain velocity v and it moves in an orbit with radius r, then we can calculate the time it takes to complete one orbit as the orbit circumference divided by the electron's velocity. The electric current is defined as the amount of charge that goes through a certain point per unit time. In this case, one electron charge passes by every time the electron completes an orbit. By using the expression for the area of the orbit, we can calculate the magnetic dipole moment of the orbiting electron. With the expression for the angular momentum of the electron, we can calculate the gyromagnetic ratio, which is the ratio between the magnetic dipole moment and the angular momentum. We see that this quantity, the electron charge divided by twice the electron mass, also occurs in the frequency shift in the normal Zeeman effect. With these results, we can find an additional interpretation of this frequency shift. Suppose we have an orbiting electron that has a certain angular momentum and a magnetic dipole moment that is equal to the gyromagnetic ratio times the angular momentum. If we apply a magnetic field at some angle with the magnetic dipole moment, then it exerts a torque that is perpendicular to the magnetic dipole moment and the magnetic field. As a result, the angular momentum vector starts rotating, or precessing, around the magnetic field. To calculate the rate of this precession, we calculate the magnitude of the torque vector. The angular momentum vector traces out a circle, so we can express its rate of change as the radius of that circle times the angular velocity. We can rewrite the right-hand side of the equation by using the definition of the gyromagnetic ratio. By cancelling out the common factor on both sides of the equation, we find that the angular frequency of the Larmor precession, or the Larmor frequency, is equal to the gyromagnetic ratio times the magnetic field strength. When we substitute the expression for the gyromagnetic ratio, we find that the Larmor frequency is equal to the frequency shift in the normal Zeeman effect. We introduce one final quantity that is related to the gyromagnetic ratio. The magnetic dipole moment of an orbiting electron is equal to the gyromagnetic ratio times its angular momentum. But from the Bohr model of the atom, we know that the angular momentum is quantized in units of the reduced Planck's constant. Therefore, the magnetic dipole moment is quantized in units of the gyromagnetic ratio times the reduced Planck's constant. This unit of magnetic moment is called the Bohr magneton. Now that we have covered the preliminaries, let's look at how the theory of spin was developed. It was the peculiar ways in which spectral lines can split that led to the realization that a new theory was needed. For example, consider a spectral line that one finds in sodium, called the sodium D line. When we examine the spectral line, we will encounter several questions, and in answering these questions, we will learn how the theory of spin was developed. The spectral line arises from the transition between two states which have the same principal quantum number n, but different angular momentum quantum numbers L. These two states are usually denoted as 3p and 3s. The number 3 refers to the principal quantum number, and the letters p and s refer to the different angular momentum quantum numbers. The reason why these letters are used is historical. It has to do with how different series of spectral lines appear to early observers, who were not yet aware of these quantum numbers. The fact that a transition between these two states yields a spectral line already raises a question. Why do these states with the same principal quantum number n have different energies? Did we not say that in the Bohr model of the atom only the principal quantum number n determines the energy, and changing the other quantum numbers give different orbits with the same energy? That is the first question. If we investigate further, we encounter more questions. For example, if we zoom in on the spectral line, we find that the line actually consists of two separate lines that are very close together. This is called the fine structure of the spectral lines. So the second question is, why do we see this pair of lines, which is also called a doublet? When we apply a weak magnetic field, each line splits in multiple lines. This is the Zeeman effect. However, the lines don't split in three, as we saw previously. Therefore, this is called the anomalous Zeeman effect, as opposed to the normal Zeeman effect. The question is, why don't we see the normal Zeeman effect? And how can we explain the anomalous Zeeman effect? Next, we can increase the strength of the magnetic field. We then see that the spectral lines will rearrange themselves such that they form a normal Zeeman triplet, where each line in the triplet consists of two closely spaced lines. This is called the Paschen-Back effect. So the question is, why do we observe the normal Zeeman effect again when we increase the magnetic field strength? Let's address the first question. How can orbits with the same principal quantum number have different energies? We saw that in the hydrogen atom, the angular momentum quantum number changes the shape of the electron's orbit, but not the energy. This is because the hydrogen atom is very simple, consisting only of one electron orbiting the nucleus, which is one proton. In more complicated atoms, however, there are multiple electrons. The outer electron therefore not only orbits around a positively charged nucleus, but also the negatively charged inner electrons. The negative charge of the inner electrons are shielding the outer electron from the positive charge of the nucleus. So the outer electron sees effectively a lower positive charge, which increases its energy. But if we decrease the angular momentum quantum number, then the orbit of the outer electron penetrates the cloud of inner electrons, so the positive charge is not always shielded by the inner electrons anymore. Therefore, the energy of such an orbit is lower. We now know that electrons do not move in well-defined orbits, but are instead spread out wave functions. Also with Schrödinger's wave functions, it can be shown that for lower angular momentum quantum numbers, the wave function of the outer electron penetrates more the wave functions of the inner electrons. Now let's answer the other questions. Why does the single spectral line turn out to be two closely spaced lines when we increase the resolution? We know that the spectral line is the result of an electron transitioning between two energy levels. So if the spectral line is split in two, it means that the energy level is split in two. But why is the energy level split in two? We know that applying an external magnetic field can split energy levels and spectral lines. But in this case, no external magnetic field is present. Therefore, we can speculate that an internal magnetic field must somehow be present inside the atom. When we do apply a weak external magnetic field, each of the two spectral lines split further into different anomalous Zeeman patterns. This means that the magnetic field splits the energy levels even further, and the splitting of one energy level is different from the splitting of the other energy level. When the magnetic field is made stronger, the spectral lines are rearranged such that they form a normal Zeeman triplet, where each line in the triplet is split. This means that the energy levels must have rearranged in such a way that corresponds to two closely spaced Zeeman triplets. The physical origins of these splittings were not understood for quite some time. First, Alfred Landé went through tons of data to find an empirical formula for the energy levels. That is, he didn't derive the formula from some fundamental physical principles, but he just tried different formulas until he found one that fits all the data. So first we're going to see what the formula says, and after that we will see how we can physically interpret the formula and how it led to the concept of electron spin. Let's first briefly recap how the normal Zeeman effect was described in the Bohr-Sommerfeld model. There are three quantum numbers: the principal quantum number, the orbital angular momentum quantum number, and a quantum number describing the z component, or orientation, of the orbital angular momentum. The orientation of the electron orbit with respect to the magnetic field determines the energy shift. To obtain the spectral lines of the normal Zeeman triplets, we introduced some selection rules that determine which transitions between energy levels can occur. Different transitions correspond to different polarizations of the spectral lines. Now let's see what formulas describe the anomalous Zeeman splitting. To describe the anomalous Zeeman splitting, Landé introduced an extra fourth quantum number s. What makes this new quantum number special is that it doesn't assume only integer values, but also half-integer values. The reason why half-integer values are necessary is because in the anomalous Zeeman effect, one spectral line can split into an even number of lines, which are positioned symmetrically around the original line. If the energy levels are determined by some quantum number that varies in integer steps, from an integer minus j to an integer plus j, then you will have an odd number of energy levels. To get an even number of energy levels, j has to be a half-integer. Therefore, the half-integer quantum number s had to be introduced to explain the anomalous Zeeman splitting into an even number of lines. With the quantum number s, we define a new quantum number j, which can have non-negative values ranging from the absolute value of L minus s to L plus s. In the same way that we had in the normal Zeeman effect a quantum number ml that varies from minus L to plus L in integer steps, we have in the anomalous Zeeman effect a quantum number mj that varies from minus j to plus j in integer steps. Whereas in the normal Zeeman effect the energy shift is proportional to the quantum number ml times the magnetic field strength B, in the anomalous Zeeman effect there is an additional factor g that depends on the quantum numbers L, s, and j. Landé found an expression for this g factor which accounts for all the experimental observations. Also for the anomalous Zeeman effect, we need to define selection rules that specify which transitions between different energy levels can occur. We can look at what happens in the special case where the new quantum number s is equal to 0. In that case, the new quantum number j can only be equal to the orbital angular momentum quantum number L. mj then runs from minus L to plus L, just like in the normal Zeeman effect. We find that the Landé g factor equals 1, because s equals 0 and j equals L, so the numerator vanishes. Therefore, we find that the energy shift in the anomalous Zeeman effect is the same as in the normal Zeeman effect. So nowadays we don't really make a distinction between the normal and anomalous Zeeman effect. There's only one general Zeeman effect, and the normal Zeeman effect is just the special case where s equals 0. Let's see how these formulas help us explain the sodium D lines. The sodium D line results from the transition between two energy levels for L equals 0 and L equals 1. To explain the observations, we assume that for both states s equals 1/2. Due to some internal magnetic field, which is yet to be explained, the energy levels are split. For the lower energy level, L equals 0, so J can only be equal to S, which is 1/2. For the higher energy level, L equals 1, so J can be either 3/2 or 1/2. The states for these different values for J respond differently to the internal magnetic field, so that's why the energy level is split in two. Now we apply a weak external magnetic field to observe the anomalous Zeeman effect. The state for which J equals 3/2 splits in 4 levels, where Mj runs from -3/2 to +3/2 in integer steps. The state for which J equals 1/2 splits in 2 levels, where Mj is -1/2 or +1/2. The same goes for the lower state, where J also equals 1/2. To find the spectral lines that result from these energy levels, we have to use the selection rules to determine which transitions can take place. For each spectral line, we can indicate whether the polarization of the spectral line is parallel or perpendicular to the magnetic field. For the transition L equals 1, J equals 1/2 to L equals 0, J equals 1/2, we obtain 4 spectral lines. For the transition L equals 1, J equals 3/2 to L equals 0, J equals 1/2, we obtain 6 spectral lines. With the formula for the Landé G factor, we find the Zeeman patterns for many other transitions as well. These can be compared to the normal Zeeman triplet, where S equals 0. These diagrams can be compared to those found in the literature. Here, the states between which the transitions can take place are not indicated by the numerical values for L and J. Rather, the values of L are denoted with the SPDF convention, and the values of J are related to the subscript. So we've seen how to calculate the energy shifts for the normal Zeeman effect, which is a special case where the new quantum number S equals 0. More generally, S can take integer or half-integer values, and we can calculate the energy shifts with the Landé G factor. In that way, we can describe the anomalous Zeeman effect. But we still need to find a formula that describes what happens in the Paschen-Back effect, which occurs when we apply a strong magnetic field. It turns out that this effect can also be described with the new quantum number S. We have 2 quantum numbers that determine the energy levels, ml, which runs from -L to +L, and ms, which runs from -S to +S. The contribution from ms to the energy shift is twice as strong as the contribution from ml. Note that also in this case, we recovered the expression for the normal Zeeman effect when we set S equals 0. We can illustrate in a diagram how the energy levels change as function of the external magnetic field strength. If no external magnetic field is applied, the states with different quantum numbers J are separated by some internal magnetic field. When a weak external magnetic field is applied, the energy levels split according to the quantum number Mj, which runs from -J to +J in integer steps. When the external magnetic field is strong, the energy levels are no longer described by the quantum number Mj, but by the 2 separate quantum numbers ml and ms. For the state with L equals 1, ml runs from -1 to +1, and because S equals 1/2, ms runs from -1/2 to +1/2. For the state with L equals 0, ml can only take the value 0, while ms still runs from -1/2 to +1/2. Note that the state with ml equals -1 and ms equals 1/2 has the same energy as the state with ml equals 1 and ms equals -1/2, because ms contributes twice as much to the energy as ml. With the selection rules, we find that there are 2 closely spaced normal Zeeman triplets. We have now seen that by introducing extra quantum numbers S and J, which can take half-integer values, we can construct formulas that describe the observed Zeeman patterns. But how do we interpret these formulas? How can we derive these formulas from more fundamental physical principles? What is the physical meaning of the new quantum numbers S and J? The first clue is found in how we define J from L and S. It suggests that we add 2 vectors for L and S together, and we find the length of the resulting vector. If the vectors for L and S are parallel, then the vector for J has maximal length. If L and S are antiparallel, the length of J is minimal. The length of J can have values in between, depending on the angle between L and S. Since the quantum number L corresponds to the orbital angular momentum, its vector should be the angular momentum vector. Then the vector for S must also be some angular momentum vector, and the vector for J is the total angular momentum vector. By considering the triangle that is formed by the three vectors, we can calculate the length of L by using the law of cosines. When we rewrite this equation, we find an expression that looks very similar to the second term in the Landé-G factor. We can rewrite the cosine of the angle as a dot product. With this result, we can express the Landé-G factor in terms of the vectors for S and J. We can define the normalized vector for J by dividing J by its length. To better interpret this expression, let's rewrite it as follows. The vector J can be written as the sum of the components of L and S along J. We can collect the terms and find that we have one component of L while we have two components of S. This looks very similar to the expression we find in the Paschen-Back effect. Therefore, we see how two very different expressions for the anomalous Zeeman effect and the Paschen-Back effect turn out to have a striking similarity. The energy shift for the Paschen-Back effect is found by projecting L plus 2s onto the magnetic field vector. The energy shift for the anomalous Zeeman effect is found by projecting J multiplied by the Landé-G vector onto the magnetic field vector. And we saw that J multiplied by the Landé-G vector can be interpreted as L plus 2s projected onto J. Now let's find the physical interpretation for these two expressions. The vector L is the angular momentum of an orbiting electron. We know that an orbiting electron has a magnetic moment μ and it generates a magnetic field B. We do not know yet where the angular momentum vector S comes from, but it stands to reason that it too has a magnetic moment and generates a magnetic field. What can then happen is that L and S affect each other through their magnetic fields. That is, the magnetic field from S causes the magnetic moment from L to undergo Larmor precession, and in the same way, the magnetic field from L causes the magnetic moment of S to precess. This interaction is called LS coupling. So the angular momentum vectors L and S are both precessing due to each other's magnetic fields. But if no other external magnetic field is present, then the total angular momentum vector J must be conserved. Therefore, we can picture the L and S vectors rotating around a fixed J vector. The projections of L and S onto J can then be interpreted as their time-averaged vector. If we assume that the gyromagnetic ratio of S is twice the gyromagnetic ratio for L, then we can interpret the term L plus 2s as the total magnetic moment of the system. If we apply an external magnetic field that is much weaker than the magnetic fields due to L and S, then L and S still mainly rotate around the total angular momentum J, but J itself will precess around the external magnetic field. If the external magnetic field B is much stronger than the magnetic fields due to L and S, then L and S will not precess around the total angular momentum J, but around the external magnetic field B. For this reason, we directly project L and S onto B to calculate the energy shift for the Paschen-Back effect with strong external magnetic fields. But for the anomalous Zeeman effect, with weak external magnetic fields, we first project L and S onto J, after which we project the resulting vector onto B. We can visualize these two different cases in the following way. If no external magnetic field is present, L and S rotate around a fixed J. If an external magnetic field B is applied that is much weaker than the magnetic fields due to L and S, then J precesses around B, while L and S still precess around J. If the external magnetic field is much stronger than the magnetic fields due to L and S, then L and S both precess around B. This explains how the empirical formulas for the normal Zeeman effect, anomalous Zeeman effect, and the Paschen-Back effect can be derived from one single theoretical framework. However, we still haven't specified the physical origins of the angular momentum vector S. What exactly causes the internal magnetic field that interacts with the orbiting electron? One early hypothesis was that S originates from the core of the atom. The core refers to the atomic nucleus plus the inner electrons around which the outer electron is orbiting. Collectively, they possess an angular momentum S and a corresponding magnetic moment which is equal to S times the gyromagnetic ratio. The outer electron that is orbiting with an angular momentum L generates a magnetic field, which acts on the magnetic moment of S, which results in an energy shift. From the Paschen-Back effect, we know that the gyromagnetic ratio for S is twice the gyromagnetic ratio for L. The magnetic field due to the orbiting outer electron can be calculated by using the Biot-Savart law. The current is given by the electron charge divided by the orbiting time. The magnetic permeability can be related to the electric permittivity. The orbiting time is equal to the circumference of the orbit, which we assume to be circular, divided by the electron speed. The electron speed is equal to its angular momentum divided by its mass times the radius of the orbit. The magnetic field vector is parallel to the angular momentum vector. To determine the radius of the orbit, we use the fact that the Bohr radius for an atom with atomic number Z is approximately equal to the Bohr radius for hydrogen divided by Z. We can put all the results together to find the energy shift due to the interaction between S and L. We can combine some factors to simplify the final expression. Later, there came another hypothesis, namely that S does not originate from the atomic core, but that it comes from the electron itself. The electron orbits the nucleus with an orbital angular momentum L, and the electron itself possesses an angular momentum S. Now the question is, how can the electron interact with the magnetic field that it generates itself? How can L and S interact if they are of the same origin? It was this question that made Niels Bohr skeptical of the idea that the angular momentum S is a property of the electron itself. But the question can be answered as follows. We're currently looking at the system from the rest frame of the atomic nucleus, where the nucleus is at rest and the electron is orbiting around it. However, to see what fields and forces the electron is subject to, one should consider the situation from the electron's point of view. In the electron's rest frame, the nucleus is orbiting around it, with a velocity that is directly related to the orbital angular momentum L. Therefore, it creates a magnetic field that acts on S and whose magnitude is proportional to L. So, L and S are coupled, as should be the case. It was this relativistic treatment of the problem that convinced Bohr that this is a satisfactory explanation of the origin of the angular momentum S. Now we can calculate the energy shift that this physical model predicts. Just like in the atomic core hypothesis, we use the fact that the gyromagnetic ratio for S is twice the gyromagnetic ratio for L. We also use the Biot-Savart law to calculate the magnetic field due to the electron's orbital angular momentum. However, because we now consider the electron's rest frame, in which the moving nucleus generates the magnetic field, we use in the Biot-Savart law the electric charge of the positive nucleus, instead of the negative electron charge. Therefore, the electric charge is the atomic number Z times the electron charge. The calculation for the Bohr radius is still the same as in the previous calculation. So the energy shift we ultimately find differs from the previous result by a factor of z, the atomic number. So there were two hypotheses for the physical origin of the angular momentum s, and they gave different predictions for how the energy shift changes as function of the atomic number. To determine which hypothesis is correct, we simply compare these predictions to the experimental results. It turns out that the second hypothesis is consistent with the data. The angular momentum s seems to be intrinsic to the electron itself. There was also another point on which the two hypotheses gave different predictions. Wolfgang Pauli noted that if S came from the atomic core, then the Landé G factor should change as function of the atomic number z. The velocities of the inner electrons change as function of z, so due to relativistic effects, their masses should change, and so the gyromagnetic ratio should change as function of z. If S is intrinsic to the electron, then no such dependence should be observed, and indeed it is not. Therefore, Pauli concluded that the new quantum number S is a property of the electron itself. Another convincing piece of evidence for why S is a property of the electron rather than the atomic core is that with Pauli's exclusion principle, it can explain why the electron energy levels are filled the way that they are. The question is this: why do a certain number of electrons occupy higher energy levels? Why don't all the electrons drop to the lowest energy level? And how can this be explained by assigning the new quantum number S to the electron instead of the atomic core? To answer these questions, we first have to look at the periodic table of elements. On the right side of the table are the noble gases. Their defining property is that they don't undergo chemical reactions with anything. It was assumed that noble gases don't react because there are certain groups of electrons, or electron shells, which the electrons can fill. Once a shell is fully filled, the element cannot react with other elements. To find how many electrons can fit in the electron shells, we can list the atomic numbers of these noble gases and calculate their differences. Now comes the observation that was made by Edmund Stoner, which inspired Pauli to formulate his exclusion principle. Let's look at the noble gas and the corresponding alkali metal in the same row of the table, for example, argon and sodium. In argon, an electron shell that can hold 8 electrons has been filled. To explain the anomalous Zeeman patterns in sodium, we had to assume that there are 8 energy levels. So the number of energy levels is the same as the number of electrons. Therefore, it seems like one quantum state can be occupied by only one electron. This is the Pauli exclusion principle. In his Nobel lecture, Pauli explained how the observation of Stoner inspired him to formulate his exclusion principle. However, it has also been noted that Pauli actually misstated the key observation of Stoner. So these are the results that we found. To explain the anomalous Zeeman effect, Landé introduced an extra quantum number S that can take half-integer values. By seeing how S adds to the orbital angular momentum quantum number L to yield the quantum number J, we inferred that S also corresponds to some angular momentum. Pauli deduced that S is a property of the electron rather than the atomic core. Moreover, from the Bohr-Sommerfeld model of the atom, we know that there are 3 quantum numbers N, L, M because we can apply the quantization condition to the 3 spatial degrees of freedom x, y, z. Therefore, if there's a 4th quantum number S, it implies another degree of freedom in addition to the 3 spatial coordinates. At this point, it becomes hard to avoid the conclusion that the electron itself must be spinning. Just like the planets orbit the Sun and also rotate around their own axes, so too would an electron orbit around the nucleus while spinning around its own axis. But Pauli avoided drawing that conclusion. Why? It's because the math didn't work out. We derived the energy shift that should result from spin-orbit coupling. But when that calculated energy is compared to the experimentally observed energy shift, it's off by a factor 2. This mismatch with experiment was the most important objection to the hypothesis of the spinning electron, but there were other problems too. For example, if we calculate with classical electrodynamics how fast the electron should be spinning to account for the observed magnetic moment, we find it should be spinning faster than the speed of light. For this reason, the hypothesis of a spinning electron was not proposed for some time, even though it appeared obvious. Ralph Kronig proposed that the electron spins, but he was persuaded by Pauli that this hypothesis had too many problems. When Samuel Goudsmit and George Uhlenbeck published the same hypothesis, Heisenberg congratulated them on their courageous paper and asked how they explained the wrong factor of 2 in the energy shift. When Llewellyn Thomas explained where the factor of 2 comes from, Pauli was finally persuaded to accept the idea of electron spin. So how did Thomas explain the factor 2 error? It has to do with how we transform from the rest frame of the nucleus, where the electron orbits around the nucleus, to the rest frame of the electron, where the nucleus orbits around the electron. When we calculated the magnetic field that is seen by the electron, we naively applied the Biot-Savart law to the orbiting nucleus. However, if we treat the problem more rigorously, we find out that things are not that straightforward. To move from one rest frame to another rest frame, we have to use the theory of special relativity. In the case of linear motion, we can switch between reference frames by using Lorentz transforms. But an orbiting electron isn't moving linearly. It's always accelerating. This acceleration makes the transforming between reference frames much less trivial, and solving this problem rigorously would take a considerable amount of effort. So instead, let's for now consider a simplified argument which makes it plausible that a proper relativistic treatment will indeed yield the factor 2 difference that we are looking for. Let's first change the circular motion of the electron into linear uniform motion. The electron constantly sees the electric field from the nucleus from one side, so it's as if it's moving in a uniform electric field that is perpendicular to the electron's motion. However, this situation is not physically possible. The electron wouldn't be able to move in a straight line, because it should be deflected by the electric field. To make the electron move uniformly in spite of the electric field, a magnetic field should be present, such that the Lorentz force counteracts the electric force. Now that the electron is moving linearly, we can use the familiar theory of relativity to straightforwardly transform to the electron's rest frame. In the electron's rest frame, there cannot be any electric field, because if there were, the electron would have to accelerate. There can only be a magnetic field, because it doesn't exert any force on a stationary electron. We use the known formula from special relativity to calculate the magnetic field in the new reference frame. We can Taylor expand this in powers of the velocity v and substitute the expression for the magnetic field strength. We can simplify the expression and use the fact that the electric field follows Coulomb's law. We can calculate the magnetic field that is due to the electron moving through the electric field of the nucleus, and see that it differs from our original result by a factor 2, exactly as we wanted. This result convinced Pauli that electrons indeed possess a property that could be interpreted as spin. After Heisenberg's matrix mechanics and Schrödinger's wave mechanics had been developed, Pauli worked out the mathematical quantum mechanical theory of electron spin. To understand how this theory works, let's briefly recap the basics of matrix mechanics. In matrix mechanics, observables such as position, momentum, and angular momentum are described by matrices. If we have a vector, then each entry of that vector is a matrix. The squared length of the vector is found by squaring and adding all entries, so this will also give a matrix. When we compute a cross product, for example to calculate the angular momentum vector, we have to apply matrix multiplications. What's important to keep in mind is that matrix multiplications in general don't commute. The commutator of a position variable and its corresponding momentum variable is given by the canonical commutation relation. However, a position variable does commute with other position variables and their momenta. We will use these principles to derive some important rules for the angular momentum operator. This is necessary to understand the theory of spin, because we know that spin is a form of angular momentum. First, we will derive the commutation relations for the different components of the angular momentum vector. We can fill in the expressions for the x and y components of angular momentum and expand the brackets. Some terms cancel out, because all factors in that term commute with each other. For the remaining terms, we have to apply the canonical commutation relation to simplify the expression. We identify the remaining factor as the z component of the angular momentum. So the commutator of the x and y components is proportional to the z component. The commutators for the different combinations of components can be found similarly. Next, we will calculate the eigenvalues of the z component of the angular momentum vector and the squared length of the angular momentum vector. We do this by introducing an operator called the ladder operator. It is named so because, as we will see, it can lower or raise eigenvalues. Let's assume we have an eigenstate psi of Lz, with corresponding eigenvalue lambda. What happens when we apply the ladder operator to the eigenstate, and apply Lz to the resulting vector? We can switch the order of Lz and the ladder operator by subtracting the commutator. To calculate the commutator of the ladder operator and Lz, we plug in the definition of the ladder operator. We use the commutation relations we found for the components of the angular momentum vector. We recognize in the resulting expression the definition of the ladder operator. We can substitute this result for the commutator and use the fact that psi is an eigenstate of Lz with eigenvalue lambda. We conclude that if we apply the ladder operator to an eigenvector of Lz, we obtain another eigenvector, but one whose eigenvalue has been raised or lowered by the reduced Planck's constant h bar. So we can raise and lower the eigenvalue of Lz by applying the ladder operator. But we shouldn't be able to do this indefinitely. In the classical case, if a particle has a certain total angular momentum L, then the z component of the angular momentum cannot be larger than L or smaller than minus L. So let's try to find the maximum eigenvalue of Lz in relation to the eigenvalue of the squared total angular momentum operator L squared. Suppose we have the eigenstate psi max that has the maximum eigenvalue lambda max. We shouldn't be able to find an eigenvector with an even higher eigenvalue by applying the raising ladder operator. Therefore, if we apply the raising operator to the eigenstate with maximum eigenvalue, we expect to find the zero vector. To see how the maximum eigenvalue for the z component of the angular momentum vector relates to the eigenvalue of the squared total angular momentum, we calculate the product of the raising and lowering operator. We plug in the definition of the ladder operator and expand the product. We use the fact that the squared total angular momentum equals the sum of the squares of all components. We move some terms to the other side of the equation. Now we can apply the squared angular momentum operator to the eigenstate with the maximum eigenvalue, and substitute the expression we just found for L squared. To simplify the expression, we use the fact that applying the raising operator to the eigenstate with maximum eigenvalue gives 0, and applying Lz to the eigenstate gives the eigenvalue lambda max. So we found how the maximum eigenvalue of the Lz operator relates to the eigenvalue of the L squared operator. We can perform the same calculation for the eigenstate with minimum eigenvalue, to find how the minimum eigenvalue of the Lz operator relates to the eigenvalue of the L squared operator. So now we have two equations involving the maximum and minimum eigenvalues of the Lz operator. If we can demonstrate that applying the ladder operator to the Lz eigenstate doesn't change its eigenvalue for the L squared eigenstate, then we can relate the minimum eigenvalue to the maximum eigenvalue. So let's demonstrate that applying the ladder operator to an eigenstate of the L squared operator doesn't change its eigenvalue. To do this, we first demonstrate that the L square operator commutes with the Lx operator. We can write out the expression for the L squared operator, and note that Lx commutes with itself. So we only need to calculate the commutators with Ly squared and Lz squared. We write down the definition of the commutator and then switch the order of the factors in each term. We can cancel two terms and plug in the result we found for the commutator of the angular momentum operators. In the same way, we can calculate the commutator with Lz squared. We see that the two commutators cancel each other out, so Lx commutes with the L squared operator. By the same argument, Ly should commute with L squared as well, and therefore the ladder operator commutes with L squared. Now let's show that applying the ladder operator to an eigenstate of L squared gives another eigenstate, but with the same eigenvalue. Suppose we have an eigenstate psi with eigenvalue mu. We can switch the order of L squared and the ladder operator, because we just demonstrated that they commute. We use the fact that psi is an eigenvector of L squared with eigenvalue mu. We find the result that we wanted. Applying the ladder operator to an eigenvector of L squared yields another eigenvector, but with the same eigenvalue. Let's summarize what we have found. The operator for the z component of the angular momentum vector has some minimum eigenvalue, and by applying the raising ladder operator to the eigenstate, we can incrementally increase the eigenvalue in steps of h bar until we reach the maximum eigenvalue. These eigenstates of Lz are also eigenstates of L squared, but they all have the same eigenvalue. Therefore, we can find a relation between the maximum and minimum eigenvalues of Lz. Since the maximum eigenvalue must be larger than the minimum eigenvalue, we conclude that the minimum eigenvalue is the negative of the maximum eigenvalue. We can thus define a quantum number m that increases in integer steps from -L to L, and the eigenvalue of Lz is given by h bar times m. L and m are the quantum numbers that were already known from the Bohr-Sommerfeld model of the atom. Furthermore, we find that the eigenvalue for the square total angular momentum operator is proportional to L times L plus 1, as opposed to L squared, which one would expect intuitively. It is for this reason that we didn't find squares in the Landé G-factor, but rather terms like L times L plus 1. Now that we are familiar with some properties of the angular momentum operator, we can formulate the mathematical theory of spin, which is also a form of angular momentum. For the angular momentum operators, we found the commutation relations, the ladder operators which raise and lower the eigenvalues by h bar, and the quantum numbers for the z component of the angular momentum and the square total angular momentum. Now we're going to impose all these results on the spin operator as well. We know that the spin quantum number can take half-integer values. For the simplest case of s equals 1/2, the z component has only two eigenvalues, plus or minus 1/2. So the matrix representations for the spin operators should be two-dimensional. We can write down the 2x2 matrices that satisfy the commutation relations and for which the z component has the correct eigenvalues. If we ignore the factor of h bar over 2, we get the Pauli spin matrices. Using the definition of the ladder operators, we can calculate their matrix representations. If we calculate the eigenstates of the SZ operators and apply the ladder operators to them, we see that indeed the ladder operators change the states such that their eigenvalues are either raised or lowered by h bar. We can also calculate the matrix for the square total spin operator by plugging in the spin matrices. We can verify that its eigenvalue is h bar squared times s plus 1. So we verified that the Pauli matrices satisfy all the properties for angular momentum operators. We can use this theory of spin matrices to explain why a single spectral line is actually split in two. For a spin 1/2 particle, the quantum number ms can take two values, plus or minus 1/2. These two states undergo different energy shifts due to spin-orbit coupling, and therefore the energy level and the spectral line are split in two. This double spectral line is called a doublet. However, it also happens that the spectral line is not split in two. Such a line is called a singlet. Or a spectral line can be split in three, which is called a triplet. When a weak external magnetic field is applied, the lines split in different kinds of Zeeman patterns. These patterns can be explained by assigning different values for the new spin quantum number s. For the singlet, where s equals 0, we get the normal Zeeman pattern, whereas for higher values of s, we get the more complicated anomalous Zeeman patterns. But how can we have different values of s? If the electron is a particle with spin 1/2, then how can we also have s equals 0 or s equals 1? To answer this question, we have to look at the states of multiple electrons, whose spins are added together. To understand how the spins of multiple particles can combine, we must find the operator for the total spin. We have the operators for the spin components of a single spin 1/2 particle. If we have two spin 1/2 particles, we add the operators of the two particles together. To find the total spin operator of the two particles combined, we add the squares of the x, y, z components together. But what does it mean exactly to add two operators together if they act on two different particles? Each particle has its own two-dimensional vector, which can be expressed as a linear combination of the spin-up and spin-down basis vectors. Now consider the spin x operator for a two-particle system. That is, the operator acts on a system of two particles, but it affects only the first particle. For example, if it acts on the state where both particles are in the spin-up state, then it flips the state of the first particle, but leaves the spin of the second particle unchanged. For all combinations of spin-up and spin-down for the two particles, we can see how the spin x operator for the first particle changes the state. Similarly, we can see how the spin x operator for the second particle changes all the two-particle basis states. To find how we can represent these operators as matrices, we need to represent the basis states for the two-particle system as vectors. By seeing how the operator transforms one basis vector into another, we can write down the matrix representation of the operator that acts on the first particle. Similarly, we can write down the matrix representation of the operator that acts on the second particle. To find the matrix operator of the total spin x component of the two-particle system, we simply add the two matrices together. From the spin x operator for a single particle system, we found the spin x operator for a two-particle system. We will now see how this action can be described more compactly as a tensor product. The two-particle operator is given by the tensor product of two single-particle operators. And in this case, one of the single-particle operators is the identity operator, which leaves the single-particle state unchanged. Here is what we do when we take the tensor product. We take the entries of the first single-particle operator, and each entry we multiply with the second single-particle operator. By putting the four matrices together, we find the matrix for the two-particle operator. We can do the same for the case where the spin x operator acts on the other particle. Then we can add the two operators together to find the total spin x operator for the two-particle system. We have now found the matrix for the total spin x operator. Now we can find the total spin y and spin c operators in the same way. We calculate the tensor products of the single particle states, and then we add the operators for the two particles together to find the operators for the total spin y and z components. To find the squared total spin operator for the two-particle system, we can simply square the matrices we found for the total x, y, z components and add them together. Now that we have found the matrix for the squared total spin, we can calculate its eigenvectors and eigenvalues. One eigenvector with eigenvalue 2h bar squared corresponds to the state where both particles are in the spin down state. Another eigenstate with the same eigenvalue corresponds to the superposition of states where the two particles have opposite spin. The final eigenstate with eigenvalue 2h bar squared is where both particles are in the spin-up state. But there is also an eigenstate with eigenvalue 0. In this eigenstate, we also have a superposition of states where the particles have opposite sign, but now the superposition has a minus sign instead of a plus sign. So we have three eigenstates with eigenvalue 2h bar squared, and one eigenstate with eigenvalue 0. Now recall the properties we found for angular momentum operators in general, and spin operators in particular. The eigenvalues of the square total spin operator are equal to h bar squared times s plus 1. Therefore, the two sets of eigenstates we found correspond to total spins of 1 and 0. These spin values correspond to the triplet states and singlet state respectively. We also recall that the quantum number ms is given by the eigenvalues of the spin z operator. When we apply the spin z operator to the eigenstates that we found, we see that for s equals 1, ms runs from minus 1 to 1, and for s equals 0, ms equals 0. This is consistent with what we expect for quantum numbers for angular momentum. Now let's introduce some new notation. We can describe a quantum state by its total spin s and spin z component ms. For example, the single particle spin-up state has total spin 1/2 and z component 1/2. The single particle spin down state has total spin 1/2 and z component minus 1/2. The triplet states all have total spin 1 and z components that go from minus 1 to 1. The singlet state has total spin 0 and z component 0. But the triplet and singlet states are two particle states, which can be represented as two single particle states. For example, the state with spin 1 and z component 1 is the result of two particles with spin 1/2 and z component 1/2. All the other states can also be written in terms of states with spin 1/2 and z component plus or minus 1/2. The way in which a total angular momentum state can be decomposed into its constituents is described in the table of Clebsh-Gordan coefficients. In the table, the two angular momenta which are to be added are specified. These two angular momenta could be the spins of two particles, as we saw previously. but they could also refer to the spin and orbital angular momenta of a particle. Next, we create a block for each value that the total z component can have. For each value of the total z component, we specify the total angular momentum. We then write down the z components of the two individual particles. Finally, we fill in the coefficients with which we should add the two particle states to find the total angular momentum state. For simplicity, we omit the square roots in the weights. Now that we have developed a theory of spin, let's see if we can derive the results for the anomalous Zeeman effect and Paschen-Back effect from fundamental theoretical principles. For example, can we derive that for the anomalous Zeeman effect we have to work with the quantum number mj, whereas for the Paschen-Back effect we have to work with ml and ms? And can we derive the expression for the Landé G factor? To derive these results, we have to use perturbation theory. The unperturbed Hamiltonian consists of two energy contributions: the kinetic energy of the electron and its potential energy due to the electric charge of the nucleus. For the energy contribution due to the spin of the electron, we have to move from the rest frame of the nucleus to the rest frame of the electron. Then we find the energy contribution that is due to spin-orbit coupling, where we have to take into account the Thomas correction factor of 1/2. This is one perturbation to the Hamiltonian. It causes the spectral line to split into a doublet. The other perturbation is due to the external magnetic field. If it's weak, it causes the anomalous Zeeman splitting, and if it's strong, it yields a normal Zeeman triplet, as described in the Paschen-Back effect. The energy is calculated by taking the inner product of the magnetic moments with the magnetic field. The magnetic moments can be related to the angular momenta via the gyromagnetic ratios. So we have the unperturbed Hamiltonian and two perturbation terms. These perturbations cause the spectral lines to split in various ways. We know from empirical observations that we need to use different quantum numbers to describe the different splitting patterns. In the following, we will see that these particular choices of quantum numbers can be explained with perturbation theory. To explain the splitting of a spectral line into a doublet, we apply the spin-orbit coupling term as a perturbation. For the anomalous Zeeman effect, the term due to the external magnetic field is an additional perturbation that is weaker than the spin-orbit term. For the Paschen-Back effect, the term due to the external magnetic field is much stronger than the spin-orbit term, so the spin-orbit term becomes the smaller perturbation. We saw in a previous video that if the perturbation lifts a degeneracy, then we have to be careful in choosing the states that we perturb. Let's briefly recap the reason for why this is so. If there is a degeneracy, it means that there are two different eigenstates of the unperturbed Hamiltonian that have the same eigenvalue, or the same energy. When we apply the perturbation to the Hamiltonian, then the eigenstates are perturbed, and the energies are perturbed in such a way that they are now different. This means that the degeneracy is lifted. Eigenstates which first had the same energy now have different energies. But this result is only true if we apply the perturbation to the right eigenstate. By that we mean the following. If we have two eigenstates with the same eigenvalue, then any linear combination of those eigenstates is also an eigenstate with the same eigenvalue. But if we start with such an eigenstate and we then perturb the Hamiltonian, then we don't end up in an eigenstate, but rather in a linear combination of eigenstates which now have different energies. So that's the difference between the right eigenstates and the wrong eigenstates for perturbation theory. The right eigenstates remain eigenstates after applying the perturbation, whereas the wrong eigenstates are not eigenstates anymore after applying the perturbation. Whether an eigenstate is right or wrong depends on what perturbation we are applying. When we have found the right eigenstate, then we can apply perturbation theory as if no degeneracy were present. So let's see how we find the right eigenstates. If there is no degeneracy, we can find the perturbation to the energy as follows. We write down the eigenvalue equation for the unperturbed Hamiltonian. Then we write down the eigenvalue equation for the perturbed Hamiltonian. We add perturbation terms to the Hamiltonian, the eigenstate, and the energy. If the perturbation is small, we can ignore the terms that are quadratic in the perturbation, and we take the inner product with the unperturbed eigenstate. We find that the perturbation to the energy is found by sandwiching the perturbing Hamiltonian between the bra and ket of the eigenstate. If there is a degeneracy, then we can consider two eigenstates with the same eigenvalue. A linear combination of these two states is still an eigenstate of the unperturbed Hamiltonian. When we perturb the Hamiltonian, then the eigenstates are perturbed, and the eigenvalues can be perturbed in different ways for the different eigenstates. Just like in the non-degenerate case, we ignore the terms that are quadratic in the perturbation, and we take the inner product with the first eigenstate and with the second eigenstate. If sandwiching the perturbing Hamiltonian between the bra and ket of the two different eigenstates yields 0, then we obtain the same equation as in the non-degenerate case. So that is the condition that must be met for the right eigenstate. We can demonstrate that the condition is met if the following is true. First, we have an operator A that commutes with both the unperturbed Hamiltonian and the perturbed Hamiltonian. So it is a quantity that is conserved both before and after the perturbation is applied. Second, the two eigenstates of the unperturbed Hamiltonian are also eigenstates of the operator A, but their eigenvalues for A are different, as opposed to their eigenvalues for the Hamiltonian. In that case, we can sandwich the commutator of A and the perturbation to the Hamiltonian between the two eigenstates, and calculate the results in two different ways. First, we note that the outcome must be 0 because the commutator is 0 by assumption. Second, we can write out the commutator and use the fact that the two eigenstates of the Hamiltonian are, by assumption, also eigenstates of A. We can rewrite this expression and observe that it must equal 0. Since the two eigenvalues are different by assumption, it must follow that the other factor in the expression must be 0, which is what we wanted to achieve. Therefore, to find the eigenstates of the Hamiltonian that are suitable to apply perturbation theory to, we must find an operator A that commutes with the Hamiltonian and its perturbation. That is, the operator A represents a quantity that is conserved both before and after applying the perturbation. The degenerate eigenstates of the Hamiltonian must be non-degenerate eigenstates of the operator A. We now apply this result to the perturbations from spin-orbit coupling and the external magnetic field. If no external magnetic field is present, the only perturbation is the spin-orbit interaction. This creates an internal magnetic field that causes the spectral line to split into a doublet. In this case, the total angular momentum vector J is conserved, while the orbital angular momentum L and spin angular momentum S are precessing around it. Because the total angular momentum vector J is constant, both its squared length and its c component are conserved. For different values of the total angular momentum, we get different values for the spin-orbit coupling energy. Therefore, the eigenvectors of the J² operator are suitable to apply perturbation theory to. The z component of the J factor is not a suitable operator for perturbation theory, because the spin-orbit coupling energy does not depend on the orientation of the J factor. The orientation of the J factor does start to matter when we apply an external magnetic field, which we assume is pointing in the z direction. If this magnetic field is weak, then it is a good approximation to say that the J factor precesses around the magnetic field, while its component parallel to the magnetic field is conserved. Therefore, the Jz operator is a suitable operator for perturbation theory. When the external magnetic field is much stronger than the magnetic interaction between the orbital and spin angular momentum, then S and L will precess independently around the magnetic field while their C components are conserved. Therefore, in this regime, the SZ and LZ operators are suitable operators for perturbation theory. To demonstrate more rigorously that these statements are indeed true, we must show that these operators commute with the perturbations to the Hamiltonian. First, let's show that the spin-orbit Hamiltonian commutes with the total angular momentum vector J, from which it follows that this vector is conserved, and that therefore its squared length and C component are conserved. To show that the vector J commutes with the spin-orbit Hamiltonian, we look at each component of the vector separately. Let's look at the x component. We can first consider the x component of the S vector. When we calculate its commutator with the spin-orbit Hamiltonian, we only have to look at the commutators with the y and c components, because the spin x component commutes with itself. We can calculate the two commutators and recognize that the resulting expression is the x component of the cross product of S with L. This is what we get when we calculate the commutator of the spin-orbit Hamiltonian with the spin x component. If we consider all other components as well, we find that the commutator of the spin-orbit Hamiltonian with the spin vector is proportional to the cross product of S and L. For the commutator with L, we interchange the role of L and S, so we find the cross product of L and S. To find the commutator with the total angular momentum vector J, we add the commutators we found for S and L, which gives 0. So we demonstrated that the spin-orbit Hamiltonian commutes with the total angular momentum vector. To show that the spin-orbit Hamiltonian also commutes with J squared, we first demonstrate that it commutes with L squared. In our discussion of the ladder operators, we already saw that the L squared operator commutes with each component of the L vector. Therefore, L squared commutes with the spin-orbit Hamiltonian. Similarly, S squared also commutes with the spin-orbit Hamiltonian. To calculate the commutator with J squared, we write it in terms of L squared, S squared, and S dot L. The commutator of J squared is therefore given by the sum of three commutators. We just showed that the commutators of S squared and L squared are 0. S dot L of course commutes with itself. So we find that the commutator of the J squared operator with the spin-orbit Hamiltonian equals 0. Alternatively, we can observe that J squared is the sum of the squares of the components of J, and we know that each component commutes with the spin-orbit Hamiltonian. So we have demonstrated that J squared and Jz both commute with the spin-orbit Hamiltonian, so they are suitable operators for perturbation theory if the Hamiltonian is perturbed by the spin-orbit Hamiltonian. Now we will look at what happens if the system is perturbed by an external magnetic field. If the external magnetic field is so strong that we can ignore the spin-orbit coupling, or the internal magnetic field, then the components of L and S that are parallel to the magnetic field are conserved. This can be verified by observing that LZ and SZ commute with the perturbing Hamiltonian, assuming that the external magnetic field points in the Z direction. But what if the external magnetic field is not much stronger than the internal magnetic field? What if we have a weak external magnetic field, so that the spin-orbit Hamiltonian is considerably stronger than the external magnetic field Hamiltonian? We use the eigenstates of the J squared operator to describe how spin-orbit coupling lifts the degeneracy, because the J squared operator commutes with the spin-orbit Hamiltonian. However, the J squared operator does not commute with the external magnetic field Hamiltonian. This does not need to be a big problem if the external magnetic field Hamiltonian is much weaker than the spin-orbit Hamiltonian. In that case, we can approximate the external magnetic field Hamiltonian as follows. the orbital angular momentum plus twice the spin angular momentum can be written as the total angular momentum plus the spin angular momentum. If there is spin-orbit coupling, the total angular momentum vector is constant, while the L and S vectors precess around it. The average of the precessing S vector is found by projecting S onto J. If in the external magnetic field Hamiltonian we replace the spin vector with the average spin vector and plug in the expression we just found for it, we find an approximate expression for the external magnetic field Hamiltonian. This Hamiltonian does commute with the J² operator, as we will demonstrate now. We've already demonstrated that the total squared angular momentum operator commutes with each of the angular momentum components. We also know that J², like any other operator, commutes with itself, and therefore with any functions of itself. So we only need to demonstrate that J² commutes with S dot J. We can write J as S plus L, and we can expand the dot product. The second term, S dot L, is the spin-orbit Hamiltonian, and we already demonstrated that it commutes with J². For the first term, we can expand J². S² clearly commutes with the first two terms, L² and S². We already demonstrated that S² commutes with the spin-orbit Hamiltonian. Therefore, this term also vanishes, and we have demonstrated that J² commutes with the approximate expression for the external magnetic field Hamiltonian. With these results, we can derive the Landé G factor, which had first been found empirically. We take the approximate Hamiltonian for the external magnetic field and calculate the energy perturbations by sandwiching the perturbing Hamiltonian between the eigenstates of the original Hamiltonian. These eigenstates are chosen such that they satisfy the requirements as formulated by degenerate perturbation theory. We can rewrite S dot J in terms of the operators J², S², and L². When we apply these operators to the eigenvectors, we obtain the eigenvalues J times J plus 1, S times S plus 1, and L times L plus 1. This yields the expression for the Landé G factor. To further incorporate spin in the theory of quantum mechanics, we construct the Pauli equation. This equation is basically Schrödinger's equation, but which includes the effect of electromagnetic fields and spin. To see how we can incorporate electromagnetic fields in the Schrödinger equation, we first see how we describe electromagnetic forces in classical Hamiltonian mechanics. We do this by starting with the equation of motion as prescribed by the Lorentz force law. From this we construct the Lagrangian, and then we find the Hamiltonian. The Lorentz force law states that a charged particle experiences a force in the direction of the electric field and a force perpendicular to the magnetic field and the particle's velocity. By Newton's second law, this force is equal to the particle's mass times its acceleration. We can rewrite this expression by writing the electric and magnetic fields in terms of the scalar potential phi and the vector potential A. We plug these expressions into the equation of motion, and then we will simplify the result by using a vector identity. Furthermore, by using the chain rule, we can relate the partial time derivative to the full time derivative. With these results, we can rewrite the equation of motion that follows from the Lorentz force law. We can further rewrite the expression by collecting the spatial derivatives and collecting the time derivatives. We can compare this equation of motion to the equation of motion that follows from the Euler-Lagrange equation. From this we infer what the Lagrangian should look like. We find the expression for the generalized momentum, and then apply the Legendre transform to find the Hamiltonian. We plug in the expressions for the Lagrangian and the generalized momentum, and then write the result in terms of the generalized momentum. We have now found the classical Hamiltonian for a charged particle in an electromagnetic field. In this Hamiltonian, we can identify the kinetic energy, where the momentum is affected by the vector potential A, and the potential energy, which is determined by the scalar potential phi. However, if the charged particle also has an internal spin that is affected by the magnetic field, then we should add an extra energy term, which is given by the inner product of the magnetic dipole moment and the magnetic field. The magnetic dipole moment is equal to the gyromagnetic ratio gamma times the spin angular momentum vector s. We saw previously that the gyromagnetic ratio for the electron spin is the electron charge divided by the electron mass, which is twice the gyromagnetic ratio for an orbiting electron. This results in the total Hamiltonian for a charged particle with spin in an electromagnetic field. Now we have to find the quantum mechanical equivalent of this Hamiltonian. We find it by replacing the momentum vector and the spin vector with their quantum operators. The momentum vector becomes the gradient operator, and the spin vector becomes a vector of 2x2 Pauli spin matrices. The wave function becomes a two-dimensional vector, where each component describes the wave function for a certain spin state. This object is also called a spinor, and it can be acted on by the 2x2 Pauli spin matrices. The Pauli equation is then given by the familiar expression that we know from the Schrödinger equation. When we apply the Hamiltonian to the wave function, we get the time derivative of the wave function. Except now the wave function consists of two spin components, and the Hamiltonian contains contributions from the electromagnetic field and the electron spin. The Pauli equation, as we wrote it down, contains both the vector potential A and the magnetic field B. But it should suffice to use only one of the two, because one is determined by the other. So in the following, we will demonstrate that the Pauli equation can be written in a more compact way, such that we only use the vector potential A and not the magnetic field B. First, we introduce shorthand notation to rewrite the first term of the Pauli equation more compactly. We can expand the dot product and then expand the square. Keep in mind that the Pauli spin matrices don't commute, and neither does the gradient operator. Therefore, we cannot straightforwardly collect the cross terms together. Rather, we use the properties of the Pauli spin matrices to simplify the terms. Then we can collect the terms again to write them in vector notation. Note that normally a cross product of a vector with itself would vanish, but in this case it doesn't, because the entries of the vectors are operators that don't commute with each other. To calculate the cross product of this vector with itself, let's consider its first component, so the x component. And since its entries are operators, we apply the result to some test function psi. We plug in the definition of the vector. We expand the product and collect the terms, and notice that some terms cancel out. We can expand the derivatives by using the product rule, and then notice that even more terms cancel out. In the resulting expression, we recognize the definition of the magnetic field B in terms of the vector potential A. Therefore, the cross product of the vector with itself turns out to be proportional to the magnetic field vector B. With this result, we can demonstrate that indeed the Pauli equation can be written more compactly in this way. We saw that Pauli used the theory of electron spin to explain why electrons are distributed over the atomic energy levels the way that they are, instead of all falling down to the lowest energy state. He postulated the exclusion principle, which states that no two electrons can occupy the same state. In the following, we will see how this principle relates to the fact that electrons are indistinguishable particles and that therefore their wave functions must have some symmetry. Paul Dirac started his argument for the indistinguishability of electrons by recalling the development of Heisenberg's matrix mechanics. Matrix mechanics was developed with the idea that the theory should only involve quantities that we can observe experimentally. For example, we can experimentally measure the frequencies of spectral lines, but we cannot directly observe the orbits of electrons in an atom. Therefore, in matrix mechanics we discard the notion of electron orbits. As we extend the theory to describe a system of multiple electrons, the same principle should still hold. The theory should not make any statements about things that cannot be measured experimentally. So let's see what this implies for systems consisting of multiple electrons. Suppose we have two electrons in different energy states. Together, they transition to two other energy states. During this simultaneous transition, they collectively emit a single photon. The question is this: can we determine experimentally which electron transitioned to which state? Let's consider one possible way in which the two electrons may have transitioned. We can calculate the frequency of the emitted photon by using Einstein's formula for the photon energy. For the other way in which the electrons may have transitioned, we can calculate the frequency of the emitted photon in the same way. We find that the photon frequency for the two transitions are the same. Therefore, they contribute to the intensity of the same spectral line, and therefore the two transitions cannot be distinguished experimentally. Following the original logic of Heisenberg's matrix mechanics, we conclude that the theory should not make any distinction between the two electrons. Electron orbits don't exist because we cannot observe them experimentally, and similarly, electrons are fundamentally indistinguishable because we are not able to distinguish them experimentally. What does this imply for the way we describe systems of multiple electrons mathematically? If we still think classically, then we can write down for a single electron the Hamiltonian, or total energy, as the sum of the kinetic energy and the potential energy. If we have a second electron, then to find the total energy of the system, we simply add the kinetic and potential energy of the second electron to that of the first. Now we interpret this Hamiltonian quantum mechanically, so it's an operator that acts on quantum wave functions. To find the states of definite energy, we have to find the eigenstates of this operator. We will demonstrate the following. If we have two eigenstates of the two single particle Hamiltonians, then the product of these two states is an eigenstate of the two particle Hamiltonian. To see why this is true, we let the two particle Hamiltonian act on the product of the two eigenstates. We plug in the expression for the two particle Hamiltonian. The Hamiltonian for a certain particle acts only on the wave function of that same particle. Since the wave functions were eigenstates of the single particle Hamiltonian, letting the Hamiltonian act on the wave function gives the eigenvalue, or the energy of the eigenstates. We can rewrite the expression to find that the product of the single particle eigenstates is an eigenstate of the two particle Hamiltonian, and its eigenvalue, or energy, is given by the sum of the two single particle energies. This makes sense when we think of the system classically. The total energy of a system of two non-interacting particles is simply the sum of the energies of the two particles. Now we will impose the requirement that the theory should treat the two electrons as indistinguishable particles. That is, we should not be able to specify which electron is in which quantum state. Mathematically, it means that we shouldn't specify which wave function is evaluated in the coordinate of which electron. More specifically, the observable quantity is the squared modulus of the wave function. So this quantity should remain unchanged if we swap the coordinates of the two particles. In fact, this must be true for all representations of the wave function, whether it's represented in the position basis, or in the momentum basis, or in the energy basis. From this it follows that upon the exchange of the two coordinates, the wave function can only change by some global phase factor. Moreover, if we swap the coordinates twice, we should get the original wave function. This means that twice the global phase shift should equal an integer multiple of 2 pi. Therefore, upon exchange of the two coordinates, the sign of the wave function must either stay the same or flip. With this symmetry requirement for the two-particle wave function, we can construct the two-particle wave function by multiplying the two single-particle wave functions evaluated in the coordinates of the two particles, and then adding or subtracting the same product, except the particle coordinates have been swapped. Now the question is, should we choose the plus or the minus sign? If we want to satisfy and explain Pauli's exclusion principle, we should choose the minus sign, which would make the state antisymmetric. This way, if both particles occupied the same single particle wave function, the two-particle wave function would be zero, so two particles cannot occupy the same state, which is exactly the Pauli exclusion principle. But not all particles obey Pauli's exclusion principle. We've seen in a previous video that to derive Planck's radiation law from photon statistics, we have to assume that the photons are identical, and that multiple photons can occupy the same state. In this case, the two-particle wave function should have a plus sign, and therefore be symmetric. Such particles are called bosons, named after Bose, who together with Einstein worked out the Bose-Einstein statistics for photons. The particles that do satisfy Pauli's exclusion principle have antisymmetric wave functions, which have a minus sign. These particles are called fermions, named after Enrico Fermi, who together with Paul Dirac worked out the Fermi-Dirac statistics for electrons. So far, we considered wave functions that are scalar functions. However, we saw that for a particle with spin 1/2, the wave function is described by a two-dimensional spinner, with one component for spin up and one component for spin down. We saw that if we have two spin 1/2 particles, they could be in one of the triplet states, which have total spin 1, or they could be in the singlet state, which has total spin 0. Note that the triplet states are symmetric, while the singlet state is antisymmetric. The total two-particle wave function of two particles with spin 1/2 consists of a function describing the spatial distribution of the wave function and of a function describing the spin. In this example, we chose the spin part to be the singlet state, which is antisymmetric. To make the full wave function antisymmetric, we see that we now have to choose the plus sign for the spatial part of the wave function. This is the opposite of what we found previously, when we ignored the spin part of the wave function. So we can make the following observation. To make the total wave function antisymmetric, either the spatial part has to be symmetric and the spin part antisymmetric, or the other way around. So far, these symmetry requirements for the wave function all sound like some purely mathematical formality. But in the following, we will see how these symmetries and antisymmetries lead to physical predictions, which can be verified experimentally. We will be comparing three two-particle wave functions, one which assumes distinguishable particles, one which assumes indistinguishable particles that don't satisfy the exclusion principle, so the wave function is symmetric, and one which assumes indistinguishable particles that do satisfy the exclusion principle, so the wave function is antisymmetric. For all three cases, we will calculate the average squared distance between the two particles. First, we rewrite the average squared distance between the two particles by expanding the square. Then, we express each average, or expectation value, as an integral of the squared modulus of the wave function, because by Born's rule, the squared modulus of a wave function represents a probability distribution. We define the average positions for the single particle wave functions, and the average squared position of the single particle wave functions. Then, for distinguishable particles, we can express the average squared distance between the particles in terms of single particle averages. When we plug in the wave function for indistinguishable particles into the expressions for the average values, then we will encounter the following cross terms. The inner product of the two single particle wave functions vanishes if we assume that they are different energy eigenstates, which are orthogonal. The other cross term is an integral that describes the spatial overlap of the two wave functions. So for the average squared distance between two indistinguishable particles, we find an expression that is different than for distinguishable particles, and which is different depending on whether the wave function is symmetric or antisymmetric. More specifically, for indistinguishable particles, we add or subtract a term that describes the overlap between the two wave functions. So if the two single particle wave functions partially overlap, then distinguishable particles would have a certain average separation. Indistinguishable particles with a symmetric wave function would have a smaller average separation, while indistinguishable particles with an antisymmetric wave function would have a larger average separation. It may seem as if particles with symmetric wave functions attract each other, and particles with antisymmetric wave functions repel each other. So sometimes this phenomenon is called exchange force or Pauli repulsion. But since there's not actually a force present, it may be more accurately called an exchange interaction. This result can explain how atoms can form covalent bonds with each other. If two electrons from different atoms occupy a symmetric two-particle wave function, then they will be closer together. This creates a negative electric charge between the atomic nuclei. This negative charge reduces the Coulomb repulsion between the two positively charged nuclei. If the two electrons occupy an antisymmetric two-particle wave function, then the nuclei will repel each other, and the atoms won't bond. We've seen that because of the Pauli exclusion principle, the spatial part of the two-particle wave function can only be symmetric if the spin part of the wave function is antisymmetric. This means that for bonds to form, the electrons have to be in the spin singlet state. If the spatial part of the wave function is antisymmetric, then the spin part must be in the symmetric spin triplet state. It is indeed known from chemistry that the electrons in a covalent bond are in the spin singlet state. This explanation for atomic bonds is a key result in valence bond theory and quantum chemistry. So we see that the concepts of indistinguishable particles and wave function symmetries can explain experimental observations. We just saw that the covalent bonds of atoms can be ascribed to the electrons being identical particles. However, Heisenberg had previously described the same phenomenon as resonance. The term resonance is still used in quantum chemistry to explain atomic bonds. Heisenberg introduced the concept of resonance to explain why there are two types of helium, orthohelium and perihelium, that have different spectral line patterns. In the following, we will explain ortho and perihelium by using the concept of indistinguishable particles and wave function symmetry, and then briefly comment on how it relates to Heisenberg's resonance. First, let's see how it was found out that there are two kinds of helium. It was known that spectral line frequencies of a spectral series are related to each other. When we take the sum or difference of two spectral line frequencies, we can predict the frequency of a third spectral line. This relation can be explained with the Bohr model of the atom. An atom has certain energy levels, and the frequency of a spectral line is given by the difference between the energy levels. If we consider frequencies from two transitions between adjacent energy levels, then we can find the third spectral frequency by summing the former two. When the spectral lines of helium were investigated, it was found that this relation didn't always hold. Rather, it appeared that there were two separate spectra. It was concluded that there are two varieties of helium, called orthohelium and perihelium, which each have their own line spectrum. We will see in the following that this can be explained by the fact that the two electrons of helium can have either symmetric or antisymmetric orbital wave functions. We saw that if the orbital wave function is symmetric, then the spin wave function must be antisymmetric, so it must be in the spin singlet state with total spin 0. If the orbital wave function is antisymmetric, the spin wave function must be in a symmetric spin triplet state, with total spin 1. To see how this leads to different energy levels, consider the Hamiltonian for a single electron that experiences the Coulomb potential of a positively charged nucleus. Then we add to it the Hamiltonian of the second electron. We now have a two-particle Hamiltonian where the electrons don't interact with each other. However, the two electrons do interact with each other because of the Coulomb interaction between them. So we have to add an extra interaction term to the Hamiltonian, which we can treat as a perturbation. The two-particle wave function for the unperturbed Hamiltonian can be either symmetric or antisymmetric, depending on the spin state. From perturbation theory, we know that the perturbation to the energy is found by sandwiching the perturbing Hamiltonian between the unperturbed wave function. This perturbation to the energy is found to be different for the symmetric states and antisymmetric states. Therefore, the helium atom will have different energy levels and therefore different line spectra, depending on whether the two-electron wave function is symmetric or antisymmetric. We know that these wave functions should correspond to either the spin singlet or spin triplet states. It is indeed observed that the perihelium spectrum consists of singlets, and the orthohelium spectrum consists of triplets. Heisenberg explained this phenomenon not in terms of indistinguishable particles and symmetric wave functions, but in terms of resonance. It can be interpreted as follows. If we have two electrons in two different energy states, then one electron can transition between states while releasing a photon. This photon has exactly enough energy to make the other electron transition between states. So the electrons have switched places. When there is resonance, the electrons are continually changing places. It could therefore be said that one cannot determine which electron occupies which state, and therefore they are indistinguishable. We saw how the anomalous Zeeman effect led to the theory of spin, and how spin explains several other phenomena, such as how electrons fill energy levels, why spectral lines can be singlets, doublets, or triplets, why covalent bonds are formed by electrons in the singlet state, and why there are two different kinds of helium with different line spectra. There are other experiments that are nowadays considered convincing demonstrations of the existence of electron spin. However, historically, these experiments were not performed to test the theory of spin, nor did they inspire the theory of spin. These are the demonstration of the Einstein-de Haas effect and the Stern-Gerlach experiment. When we list several key developments in chronological order, we see that these two experiments were performed well before the theory of spin was proposed or developed. Let's start with the Einstein-de Haas effect. Hans Christian Ørsted discovered in 1820 that an electric current generates a magnetic field. We also know that there are permanent magnets, which somehow also generate a magnetic field. André-Marie Ampère then suggested that this magnetic field is generated by molecular current loops inside the magnet. Albert Einstein and Wander de Haas tested this hypothesis by reasoning as follows. The electrons in the current loops carry angular momentum. These current loops generate the magnetic field of a permanent magnet. If we wrap a coil of wire around a ferromagnet and then let the current run through it, we can change the direction of the magnet's magnetic field. If the magnetic field now points in the opposite direction, it means that the current loops must now be going in the opposite direction. That means that the angular momentum of the electrons now have opposite sign. But we also know that angular momentum should be conserved. Therefore, we expect that the ferromagnet starts rotating to conserve the total angular momentum. The change in the magnetic field is related to the change in the electron's angular momentum via the gyromagnetic ratio. Therefore, by measuring the change in the magnetic field and the change in the angular momentum of the ferromagnet, we can experimentally determine the gyromagnetic ratio of the electrons. At first, the measurements seem to indicate that the measured gyromagnetic ratio matches the one that can be calculated theoretically for an orbiting electron. However, later, more accurate measurements indicate that the gyromagnetic ratio is twice as large. According to the theory of spin, the electron's spin angular momentum has a gyromagnetic ratio that is twice as large as that of its orbital angular momentum. Therefore, it can be concluded that the magnetic field of a magnet is mainly generated by electron spin, rather than the electron's orbital motion. Now let's look at the Stern-Gerlach experiment. This experiment was originally performed to test the Bohr-Sommerfeld model of the atom. More specifically, the aim was to test whether the orientation of an electron orbit was really quantized. This quantization, also called space quantization, is somewhat odd, because what makes one orientation different than another? In the absence of any external fields, with respect to what do we define the orientation of the electron orbit? So Otto Stern wanted to see if this space quantization was indeed something real. He proposed an experiment to test this. This proposal was met with skepticism by several prominent scientists. For example, Max Born always thought that space quantization was something symbolic, not something literal, so there was no sense in experimentally testing it. Peter Debye similarly thought that space quantization was never supposed to be interpreted as something physically real. Nonetheless, Stern still performed the following experiment. We saw that an orbiting electron creates a magnetic dipole. If we put this magnetic dipole in an inhomogeneous magnetic field, then the dipole experiences a net force. This is because the potential energy of a magnetic dipole in a magnetic field is given by the inner product between the two. The force is given by the gradient of the potential energy. So if the magnetic field has a non-zero gradient, then the magnetic dipole experiences a net force. To understand this intuitively, we can see how this works for an electric dipole in an electric field. If we have a homogeneous electric field, then the positive and negative charge experience forces of equal magnitude and opposite directions. Therefore, there will be a torque, so that the electric dipole aligns with the electric field. But there will be no net force on the dipole. If, however, there is a gradient in the electric field, then the positive charge will experience a force that is not the exact opposite of the force on the negative charge. So the forces don't cancel out, and the dipole experiences a net force. So suppose an atom with an orbiting electron is moving with a certain velocity. The orbiting electron generates a magnetic dipole. Now the magnetic dipole passes through some inhomogeneous magnetic field. Because there's a gradient in the magnetic field, the magnetic dipole experiences a net force, which means the atom is deflected as it moves through the magnetic field. Classically, the magnetic dipole can be oriented in any direction, and it would undergo Larmor precession as it moves through the magnetic field. Therefore, if we send in a beam of atoms with random orientations, the atoms would be deflected in many different directions. But according to the Bohr-Sommerfeld model, the magnetic dipole can only point in a few directions, so the beam of atoms would not be spread out, but split. So classically we would predict that the beam of atoms is not split, but spread out. But the experimental results showed otherwise. The beam of atoms was split in two. This seems to confirm that something quantum mechanical is happening. However, it is not quite the confirmation of the Bohr-Sommerfeld model that we were looking for, because according to that model, the electron orbit could have three different orientations, so you'd expect the beam to be split in three. So let's see how the Bohr-Sommerfeld model predicts that the beam splits in three, and how the theory of spin can explain why the beam splits in two. To explain the normal Zeeman effect, where the spin is zero, we saw that the energy levels are split according to the quantum number ml. This quantum number relates to the z component of the orbital angular momentum, so it determines the orientation of the electron orbit. The force by which such an orbiting electron is deflected in an inhomogeneous magnetic field is also proportional to the quantum number ml. We know that ml runs from -L to +L, where L is the quantum number relating to the total orbital angular momentum. Therefore, for the smallest value of L for which splitting occurs, which is for L is 1, there are 3 values of ml, so the beam of atoms is expected to split in 3. But recall that the normal Zeeman effect is just one very special case where the spin is zero. The more general case is described by the formula for the anomalous Zeeman effect, where the spin can have other values. In this case, the energy levels are determined by the quantum number mj and the Landé-G factor. The quantum number mj refers to the z component of the total angular momentum, that is, the sum of the orbital and spin angular momentum. It is with this formula that we can more generally predict the splitting of the beam of atoms in a Stern-Gerlach experiment. For all the different values of the quantum numbers L, S, and J, we can calculate how the energy levels split. We see that the splitting in two that was observed in the original Stern-Gerlach experiment corresponds to an electron state with orbital angular momentum 0 and spin quantum number 1/2. So the Stern-Gerlach experiment provides a convincing confirmation of the theory of spin. However, the experiment was not originally conducted to test the theory of spin, nor did it inspire the development of that theory. Even after the theory of spin had been developed in 1925, it somehow took another 2 years before it was realized that the result of the Stern-Gerlach experiment could be explained with spin. To conclude, let's see how we might physically interpret quantum spin. To what degree can we understand it with the help of classical analogies, and how does it fundamentally differ from classical physics? Let's first introduce some terminology. The eigenstates of the spin z operator denote the states where the spin angular momentum vector points in the +z or -z direction. So we can call these the spin up and spin down states. Similarly, we could call the eigenstates of the spin x operator the spin left and spin right states, and the eigenstates of the spin y operator might be called spin front and spin back, but that's by no means standard terminology. We find that we can write the spin up state as a linear combination of the spin left and spin right eigenstates. Therefore, if the spin vector unambiguously points in the z direction, its x component is not 0 but undefined. Similarly, if the spin vector points in the x direction, its z component is undefined. To see what this means in practice, recall Born's rule. The quantum state describes a probability distribution for the possible measurement outcomes, and once a measurement has been made, the wave function collapses to be consistent with that measurement. So let's say we measure the spin z component of the electron, for example with the Stern-Gerlach apparatus, and we find that it is in the spin-up state. Because of the measurement, the wave function has collapsed to the spin-up state, which means the electron is in a superposition of the spin left and spin right state. This means that if we measure the x component of the electron spin, we measure with 50% probability either spin left or spin right. Let's say we measure spin right. Then the electron wave function collapses to the spin right state, so it's now in a superposition of spin up and spin down. If we now measure the spin z component again, then with 50% chance we might find a result that is different from our initial spin z measurement. This seems to be a contradiction with classical physics, where you can unambiguously and simultaneously define and measure all three components of an angular momentum vector. Moreover, these three components are always real valued in classical physics, whereas in quantum physics we use complex values to describe the quantum state. Mathematically, the reason why we cannot simultaneously measure the spin x and spin z components is because their operators don't commute, so they don't share the same eigenvectors. We've seen previously another example of non-commuting operators, namely the position and momentum operators. The fact that the position and momentum of a particle cannot be measured simultaneously is commonly known as an example of Heisenberg's uncertainty principle. While this is sometimes presented as an example of quantum weirdness, it actually makes some sense if we think in terms of waves rather than particles. For example, a plane wave propagates in a well-defined direction, but it is spread out through space, so it doesn't have a well-defined position. If, however, we generate a wave by throwing a pebble in a pond, then at the moment the pebble hits the water, the position of the wave is well defined. But then the wave starts spreading out in all directions, so it doesn't propagate in a single well-defined direction. So the uncertainty relation between position and momentum can be understood by thinking in terms of waves instead of particles. In the same way, can we better understand the uncertainty relation between the spin x and spin z components by thinking in terms of waves instead of a spinning particle? It turns out that, indeed, the theory of describing electron spin is very similar to the theory of describing the polarization of light waves. The eigenstates of the spin matrices are the same as the Jones vectors of different polarization states. The Jones vectors describe how the electric field oscillates in the plane perpendicular to the propagation direction. Complex numbers are used to describe the phase delay in the oscillations of the different components. The spin z eigenvectors correspond to horizontal and vertical states of polarization. The spin x eigenvectors correspond to diagonal polarization. The spin y eigenvectors correspond to circular polarization. From this point of view, there is nothing strange about saying that one state is a linear combination of other states. To perform a polarization measurement, we use a polarizer. If we send vertically polarized light through a diagonal polarizer, then each photon can get transmitted with 50% probability, after which the photon is diagonally polarized. This is similar to when the spin x component of a spin-up electron is measured with a Stern-Gerlach apparatus. It has indeed been proposed that electron spin has a classical analogy with light polarization, and therefore spin is more a wave property than a quantum property. So can we interpret spin in purely classical terms? Or is there a way in which this is a quantum phenomenon that cannot be described classically? It has been studied to what extent a quantum computer can be simulated with fully classical wave optics. It was found that the key quantum mechanical feature is non-local entanglement. This means that particles may be at different positions, but they don't have separately defined states. For example, consider the spin singlet state of two electrons. We cannot say of one electron what spin state it is in. The two electrons share one entangled state, and we can only say that the two electrons have opposite spin, but not which electron has which spin. Mathematically speaking, an entangled state is one that cannot be factorized in single particle wave functions, because in that case each particle would have its own separate quantum state. In summary, we saw that the anomalous Zeeman effect could not be explained with the classical or quantum theories at that time. To understand this effect, an empirical formula describing the splitting of the spectral lines was constructed. The formula suggested that there was another source of angular momentum, in addition to the angular momentum of the orbiting electron. First, it was suggested that this extra angular momentum came from the atomic core, which consists of the nucleus and the inner electrons. But after further investigation, it was found that the electron itself carried internal angular momentum, which implies that it is spinning. Now that the electron was assigned an extra spin quantum number which can take two values, Pauli was able to explain why the electrons occupied the atomic energy levels the way that they do. Each quantum state can be occupied by at most one electron. The origin of the exclusion principle can be explained by the assumption that electrons are indistinguishable particles. To describe this indistinguishability mathematically, the electron's two-particle wave function must be either symmetric or antisymmetric. An antisymmetric two-particle wave function will vanish if two particles occupy the same state. The way in which electron spin is truly a quantum phenomenon and not comparable to anything classically is in that the spins of two particles can be non-locally entangled. A question still remains. Why should electrons have a spin of 1/2? To answer that question, we will have to incorporate special relativity into the theory of quantum mechanics.